Um, where was I? Here. Yeah, exactly. So I was trying to figure out whether I can replicate those graphs first. Exactly. But using the optimal parameters that my own execution outputs, and at the same time, this new library, this new notebook that the Jack released, which I was eager to basically move forward with because I did the theory part, um, and I remember the third part was a bit. Um, I remember I didn't quite follow that. Uh, Other than those are the shapes of the variables, and then this is kinetic mixer. I don't know. Well, I'll probably come back to this later. I just bum 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 bum. Yeah, exactly. So I wanted to start here. There's a small tangent on creating quadrature plots with strawberry fields and matplotlib. So I promised this section before we start creating our actual simulation. One of the best ways to visualize the state of the continuous variable is with the Wignef function, which is a 3D graph in the XP phase space. Each point analogous to the quantum mechanical probability density tells us the probability of measuring a particle's x and p quadrature values between x and x plus dx and p plus dp. Likely to reveals a fantastic built-in feature that we can use to get doing the graphs. However, for the purpose of our simulation, we will only be interested in the x quadrature probabilities, as we discussed previously. Strawberry Fields doesn't have a feature that outputs quadrature probabilities quite yet. So in order to get the probability distribution for x, we will have to integrate our Wigner function across p. Mm, okay. Now the function that returns the Wigner function in Strawberry Fields gives us a 2D array of numerical values, thus we must integrate numerically across all the points for each of the returned values of x. We can do this fairly easily by using a built-in Simpson's method function in SciPy. Let's do a quick example. Consider the preparation of this or the two Fox state in Strawberry Fields. What is these? Fox space. The Fox space is an algebraic construction used in quantum mechanics to construct the quantum states space of a variable or unknown number of identical particles from a single particle Hilbert space. Known or a known number of identical particles. Informally, a Fock space is the sum of a set of Hilbert spaces representing 0 particle states, 1 particle states, 2 particle states, and so on, if the identical particles are bosons and particle states. Technically, the Fock space is the Hilbert space completion of the direct sum of the symmetric of... Okay. Okay, so it's basically what defines the space, the mathematical space, I guess. So that creates the state 2. Now let's compose our integrating method. state weakness. So this weakness function, I guess this is sort of the CV equivalent of what? I mean, it's just what represents your. Okay, so this is what instead of the amplitude, you've got the weakness function. Instead of your discrete set of amplitudes, you've got the weakness function that basically describes the probabilities of your state. Okay. Now let's compose our integrating method. Notice that when we get points already from -4 to 4, the peak of our distribution should be around 1. So outside of this bounds, especially -4, the probability of any measurement will be practically 0. This will approximate infinite, plus minus infinite to plus minus 4. We have to integrate across each set of points with the same value of x, and this will give us the total probability of measuring that specific value of x for any arbitrary value of p. This we have. Finally, we have to plot our data as a quadrature graph. Value of x, probability. Okay. Interesting. And that's state 2. Okay. Okay. Now, this is the interesting part. So this is the same example, I think, but it's a little bit different in the sense that I think the mixer is a bit different, and the actual circuit, the actual cost part is different as well. The cost ham, which I'd be curious to know why. So maybe I'll go quickly through this, identify any potential differences, and then go ahead with trying to reproduce those graphs. At least here using the strawberry fields, because I kind of like that. And then let's see what we're getting here. So now we understand Q and VQ actually works, and implement the basic simulation of the algorithm for basic cost function. Like this one, we can easily translate this into the language of quantum custom Hamiltonians with the method outlined in the previous section to get this. Okay, so here just directly there. Okay, so for a circuit, the unitary is given as this. Okay, so now how do we? So here. Here we're getting something like that just for the cost. Here. And here you've got the cost function and already the mixer. In order to implement this on a photonic quantum circuit, we need to express these unitaries in terms of products of gates in the allowed gate set of our quantum computer. For our simulations, we'll use strawberry fields, so we're confined to the gate set that strawberry fields library provides. We can technically make custom gates, but that feels like cheating. Anyways, let's expand. You can make custom gates in strawberry fields? Really? Software strawberry fields. How can I start? Interactive. You can make custom gates. Maybe not here. Maybe just yeah, just at the code level. Okay. Okay. So let's go back. let's expand and separate. Now I hope you're saying, unless you are on step ahead of me, Jack, separating a matrix exponential, don't you need an infinite number of terms for the Baker-Campbell-Hausdorff expansion? Well, the answer is yes, but practically all of those terms end up being equal to 1. The operators these and that will commute this Baker-Campbell greatly reduces, and we get these. Okay. So it basically expands these into this. Okay, so now we get 2 for the... Okay, so that's then closer to this, yeah. 2 times A. Yeah. 2 times A. Here is just beta, and here's this other. So that should be the same. Okay, so you got into the same unitary cost unitary. We just dropped the exponential because it is overall phase and does not affect our quantum state. Conceptually, this makes sense, as a squared simply acts to shift our entire parabola vertically, not affecting the x-coordinate of the global minimum. Thus we must I guess it's might as well drop it from the cost function. We'll keep it in there for the classical post-processing. We have 2 gates that we need to act upon a photonic mode. In order to implement these unitaries on the quantum circuit, we express them as momentum displacement and quadratic phase operator. First, the momentum displacement operator is defined as Z. But wait, then here Z, P, and R. But R was used as the mixer. Okay, so yeah, I thought okay, it's the same. Okay, I don't know, for some reason I thought it was different, but I see it's the same. So okay, yeah, forget about it. It seems everything the same. It's Z and P. The R gates here are the mixer. It's just the mixer the Jack is using in this notebook is different, but that kind of makes sense. I mean, you can use different mixes, I guess. Some of them might work better than others. We have 2 gates that we need to act upon a photonic mode. In order to implement this use the unitaries in the quantum circuit, we express them as a momentum displacement and a quadratic phase operator. First, momentum displacement operator is defined as this. So we have h bar being 2, and that's the Planck constant. I was kind of, but why can you choose that? I don't know. We also utilize the quadratic phase gate with S being like this, and here, so here, okay, so here basically S is minus 4 times the parameter, and I guess it's like that because Jack assumes somewhere here that h bar is 2, and he hasn't there, so I think that's the same. And then basically 2 times this times A times h bar is the same. Here is 4 times A times this. Okay. Still, the choice of gate is kind of missing that intuitive part in here. But Guillaume mentioned that he has some slides that explain a bit more the intuition at this level, about the choice of gates and stuff like that, if I understood him well. So I might check that out as well soon. But basically that looks like, okay, it's the same. So we can code this up in Submarine fields. First we have to initialize the value of the Planck's constant, as well as the value of A. For now we will pick some arbitrary value. I chose 0.83. You can change this later if you want to convince yourself that the algorithm works for other values of A as well. Okay. We'll now define our classical cost function, which is fairly easy. Our cost unitary. Now we can turn on our attention to implementing the mixer Hamiltonian. Let's start with the kinetic mixer. Okay, so let's move to the number mixer. In order to implement this gate, we simply perform a Fourier gate operation on both sides of the quadratic phase. If the removal of those Fourier operations from the sum made you do a double take, never fear. Consider the following. Since this is the inverse of f, as the operations are unitary, the same logic follows. We can then code this into Strawberry field program with the parameter R gate, P gate, R gate. Okay. Why is this called a kinetic mixer in the first place? Where does this all come from? Boo, 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 boo. Kinetic mixer. Nice. Strawberry fields. Kinetic mixing in theory. Kinetic mixing in theory. Models with more than one. What is these? Mixes the kinetic terms of the ability. Blah. High energy such kinetic mixing may lead to interesting phenomenology in the effective flow energy theory. Okay, I don't know. So, but there's this kinetic mixer thing. A Fourier gate operation on both sides. And in Strawberry fields, so there's a Fourier gate. Okay. A Kerr gate, a cubic phase gate, a rotation gate, momentum displacement, quadratic phase, position displacement, squeezing. Oh, there's many more gates than I thought. What's a help? No, I'm more for the documentation. Software, hardware, about, company price, documentation. Fourier gate. This page, God, is so difficult to navigate. Okay, I'll go ahead. So there's an actual Fourier gate, but then this is coded using R gate, P gate, and R gate. We have a few more parameters that we have to define as well before we run our simulation. We have to choose our circuit depth, which is the number of times the cost mixer unitary is applied. and the photon cutoff dimension of our strawberry field simulation. In addition, we have to choose our squeezing parameter, which will initialize, will be initializing our simulation in a squeezed state over the X quadrature in order to ensure that algorithm searches over a large space of possible solutions. So that's I don't know if I mentioned that already, but so it seems that the S gate is exactly, I think I said that, what the Hadamard is sort of an equivalent of the Hadamard gate, and because it creates uncertainty in one side or the other, so either in the position or in the momentum, and that is a good insight for later on the Yellow Submarine project as well, because I think that's in there, but that's another thing. Defines the circuit depth, squeezing parameter. But I'm still now we have position to define our first circuit. We'll first with numerical values look for solution. Now there's not a function. We'll be using the actual optimization of the circuit. The circuit does not sample the circuit, but rather returns within a function. We'll find in addition, we'll only optimize over one parameter as a function. That's a fairly simple one. Okay, so that's what's different from here is that the Jack goes ahead and basically has then the actual generation of the function here. Why is it called alt circuit? Except instead of returning numerical in the function values, we will actually sample the circuit for individual values. Do we here start also with in a squeezed state? Yeah. How many times it runs, an objective function to minimize. The average of our repeated samples of the circuit. The classical optimizer. We're not interested in this right now. And then you've got the results in here. And then the X quadrature has spiked pretty close to the optimal point, which is marked by the orange line. Okay. You're welcome to play around with farther with other mixes, parameters, circuit depth, etc. to see what works the best for before you proceed in this notebook. But now I'm going to move into something a bit more interesting. For some reason, the optimizer does not do as well when for some reason the optimizer does not do as well when A is chosen outside the range of -1 to 1. But this can be improved by playing around with the squeezing parameters as well as the value of the Planck constant. For instance, let's increase the value of the Planck's constant to 1 and try to run the simulation for a larger value of A. I include the result as an image so I don't have to rewrite all the code below. All other parameters were kept constant except for the value of the Planck's constant, which is now -1.41. Okay. As you can see, we get pretty decent results. It's important to note that when I was playing around it, the optimizer was super finicky and sometimes it would not work. There are lots of sources of error that could account for this, including limits in classical optimizers when sampling stochastic functions, low cutoff dimensions, etc. Okay. But essentially, that's kind of the same example. It's the same example. It's just with a different mixer. So what are the parameters he's using here? But he's choosing a equals 1. The algorithm seems to work pretty well. Here's an example of the quadrature plots. When I ran the algorithm with a equals 1, I was able to generate these graphs by inputting the optimized parameters yielded from my program to the Strawberry Fields interactive simulation interface. So let's try it one more time. So a equals 1. Yeah. So the parabolic minimum equals 1. Here the h bar is set to 2 because, I mean, it's implicit in this here, right? So we got that right. Minus 2, well, yeah, whatever that is. Yeah, but it's like minus 4 minus 1 minus 4 minus 1, and this parabolic minimum times 4 times better. Yeah. Possible parameters. It's everything. Okay, parabolic min says 3 here, but doesn't matter. Cutoff dimensions 5. I got the same. Squeeze is minus 0.5. Alpha param, beta param. I mean, I copy pasted that, so what am I? When with a equals 1, right? So if I do this and get the optimal values, the optimal parameters, then I should be able to put them in here. Third step. These graphs are the following: S, Z, P, and R. Let's go with this one. Right? Okay, so here we go. So first is an S. First is an S. So S, Z, P, and R. S, Z, P, and R. Now, it's a fog simulation, cutoff dimension 5. Squeezing factor, and maybe here is, I don't know if those are this, I don't know if those map to exactly those parameters. That's the thing. Minus 0.5 and 0, right? Minus 0.5 and 0. Because polar coordinates I don't know which is which, honestly. Or a polar phone. Maybe this is it. 0. Minus 0.5 and 0. The Z gate is 4 times the parabolic minimum, which is 1, and the beta beta param 0, right? And how I'm printing them, optimal parameters. Okay, so it's the first of the second, yeah. So let me take up the calculator for a second here. We are at, it's 0.5. So it's literally, so it's actually, oh man, it's -4 times 0.5, so -2, yeah. Sorry, it's 4, not -4. It's 0. It's 4 times 0.5 is 2. So it's 2. Now the P. The P. Come on. I don't even know where my stuff is here. The P gate is -4 times the beta parameter 0. So in this case -2. -2. And the R is -1 times the alpha parameter, which in this case is 0.1. So it's -0.1. 0.1, assuming that is, you know, the way this works from parameter perspective. It's not, I'll have to dig into this, but okay. And now how can I and now there's supposed to be a measurement. Measure X. So is it? How do I get the Fox states quadratures Wigner function? Do I have to measure? It seems it's changed a bit. What the? That's fancy stuff. What? That's probably not what I want then. Quadratures, that's what I want. Go. What? It's not exactly what I was expecting though. But it's at least it's closer to these, but and it peaks at around the same point, but it's not what I was expecting. Okay, but it's better. I'll double check the video what I used last time. It's kind of, yeah, it's a bit better. It peaks at, yeah. Okay, cool. And then with the second step, third step, but it's still, so that's the third step, that's the second step, that's the, because you're doing the same. Okay, I mean, okay, I okay, I don't know. At least there's, so it's a similar pattern, but it seems a bit different. This is a bit more flaky, like okay, I don't know. We'll see. We'll think about it. But basically that's the idea, I guess. We'll try to go for the harder problem in a second video, and then at some point I'll probably kind of do an overview, because I'm just reading through and not really catching absolutely all the details, but I'm hoping that going through these, that's like a two variable. I'm interested in just how you do that from a two variable perspective. And then there's another one which is basically, what else is there? Go to the top. Quadratic function, another small high order gate decomposition. Okay. Yeah, we'll see if I can pull through. Seems it's getting pretty technical. But I just want to go through it, see what things can I kind of learn at the intuition level. I think that's definitely going to be helpful for the Yellow Submarine project, and then moving on to something else. Perfect. Cool.